5 Other effects of Ice Age glaciers. Describe and explain several important effects of Ice Age glaciers other than erosional and depositional landforms. In addition to the massive erosional and depositional work carried out by Ice Age glaciers, the ice sheets had other effects, sometimes profound, on the landscape. For example, as the ice advanced and retreated, animals and plants were forced to migrate. This led to stresses that some organisms could not tolerate. Hence, a number of plants and animals became extinct. Other effects of Ice Age glaciers that are described in this section involve adjustments in Earth's crust due to the addition and removal of ice, and sea level changes associated with the formation and melting of ice sheets. The advance and retreat of ice sheets also led to significant changes in the routes taken by rivers. In some regions, glaciers acted as dams that created large lakes. When these ice dams failed, the effects on the landscape were profound. In areas that today are deserts, lakes of another type, called pluvial lakes, formed. Crustal subsidence and rebound. In areas that were major centers of ice accumulation, such as Scandinavia and the Canadian Shield, the land has been slowly rising over the past several thousand years. Uplifting of almost 300 meters, 1,000 feet, has occurred in the Hudson Bay region. This, too, is the result of the continental ice sheets. But how can glacial ice cause such vertical crustal movement? We now understand that the land is rising because the added weight of the 3-kilometer, 2-mile, thick mass of ice caused down warping of Earth's crust. For example, scientists have determined that Antarctica's ice sheets depress Earth's crust by an estimated 900 meters, 3,000 feet, or more in some places. Following the removal of this immense load, the crust adjusts by gradually rebounding upward, figure 18.30. Figure 18.30 Crustal subsidence and rebound. These simplified diagrams illustrate subsidence and rebound resulting from the addition and removal of continental ice sheets. Sea level changes. One of the most interesting and perhaps dramatic effects of the Ice Age was the fall and rise of sea level that accompanied the advance and retreat of the glaciers. Although the total volume of glacial ice today is great, exceeding 25 million cubic kilometers, during the last glacial maximum the volume of glacial ice amounted to about 70 million cubic kilometers, or 45 million cubic kilometers more than at present. Because we know that the snow from which glaciers are made ultimately comes from the evaporation of ocean water, the growth of ice sheets must have caused a significant worldwide drop in sea level, figure 18.31. Indeed, estimates suggest that sea level was as much as 100 meters, 330 feet, lower than it is today. Thus, land that is presently flooded by the oceans was dry. The Atlantic coast of the United States lay more than 100 kilometers, 60 miles, to the east of New York City. France and Britain were joined where the famous English Channel is today. Alaska and Siberia were connected across the Bering Strait, and Southeast Asia was tied by dry land to the islands of Indonesia. Conversely, if the water currently locked up in the Antarctic ice sheet were to melt completely, sea level would rise by an estimated 60 or 70 meters. Such an occurrence would flood many densely populated coastal areas. Smart figure 18.31 Changing sea level. As ice sheets form and then melt away, sea level falls and rises, causing the shoreline to shift. Animation. Sea level changes related to formation and melting of glaciers. Your browser doesn't support HTML5 video.
The growth and decay of ice sheets significantly influences sea level and the configuration of coastlines. During the last glacial maximum about 18,000 years ago, sea level was about 100 meters, more than 300 feet, lower than at present. As you can see, the position of the coastline looked very different from today's. Here's a map of what North America would look like if present-day ice sheets were to completely melt.
Changes to rivers and valleys. Among the effects associated with the advance and retreat of North American ice sheets were changes in the routes of many rivers and the modification in the size and shape of many valleys. If we are to understand the present pattern of rivers and lakes in the central and northeastern United States, and many other places as well, we need to be aware of glacial history. Two examples illustrate these effects. Upper Mississippi Drainage Basin. Figure 18.32a shows the familiar present-day pattern of rivers in the central United States, with the Missouri, Ohio, and Illinois rivers as major tributaries to the Mississippi. Figure 18.32b depicts drainage systems in this region prior to the Ice Age. The pattern is very different from the present. This remarkable transformation of river systems resulted from the advance and retreat of the ice sheets. Figure 18.32 Changing rivers. The advance and retreat of ice sheets caused major changes in the routes followed by rivers in the central United States. Notice that prior to the Ice Age, a significant part of the Missouri River drained north toward Hudson Bay. Moreover, the Mississippi River did not follow the present Iowa, Illinois boundary but rather flowed across west-central Illinois, where the lower Illinois River flows today. The preglacial Ohio River barely reached to the present-day state of Ohio, and the rivers that today feed the Ohio in western Pennsylvania flowed north and drained into the North Atlantic. The Great Lakes were created by glacial erosion during the Ice Age. Prior to the Pleistocene epoch, the basins occupied by these huge lakes were lowlands with rivers that ran eastward to the Gulf of St. Lawrence. The large Taze River was a significant feature prior to the Ice Age, see Figure 18.32b. The Taze flowed from West Virginia across Ohio, Indiana, and Illinois, and it discharged into the Mississippi River not far from present-day Peoria. This river valley, which would have rivaled the Mississippi in size, was completely obliterated during the Pleistocene, buried by glacial deposits hundreds of feet thick. Today the sands and gravels in the buried Taze Valley make it an important aquifer. New York's Finger Lakes. The recent geologic history of west-central New York State south of Lake Ontario was dominated by ice sheets. We have already noted the drumlins in the vicinity of Rochester, see Figure 18.29. Many other depositional features and erosional effects are found in the region. Perhaps the best known are the Finger Lakes, 11 long, narrow, roughly parallel water bodies oriented north, south like fingers on a pair of outstretched hands, Figure 18.33. Prior to the Ice Age, the Finger Lakes area consisted of a series of river valleys that were oriented parallel to the direction of ice movement. Multiple episodes of glacial erosion transformed these valleys into deep, steep-walled lakes. Two of the lakes are very deep. Seneca Lake is more than 180 meters, 600 feet, deep at its lowest point, and Cayuga Lake is nearly 135 meters, 450 feet, deep, and the beds of both lakes lie below sea level. The depth to which the glaciers carved these basins is much greater. There are hundreds of feet of glacial sediment in the deep rock troughs below the lake beds. Figure 18.33 New York's Finger Lakes. The long, narrow basins occupied by these lakes were created when ice sheets scoured these river valleys into deep troughs. Satellite image courtesy of NASA, photo by James Schwabel/Alamy Images. Ice dams create proglacial lakes. Ice sheets and alpine glaciers can act as dams to create lakes by trapping glacial meltwater and blocking the flow of rivers. Some of these lakes are relatively small, short-lived impoundments. Others can be large and exist for hundreds or thousands of years. Figure 18.34 is a map of Lake Agassiz, the largest lake to form during the Ice Age in North America. It came into existence about 12,000 years ago and lasted for about 4,500 years. With the retreat of the ice sheet came enormous volumes of meltwater. The Great Plains generally slope upward to the west. As the terminus of the ice sheet receded northeastward, meltwater was trapped between the ice on one side and the sloping land on the other, causing Lake Agassiz to deepen and spread across the landscape. Such water bodies are termed proglacial lakes, referring to their position just beyond the outer limits of a glacier or an ice sheet. The history of Lake Agassiz is complicated by the dynamics of the ice sheet, which, at various times, re-advanced and affected lake levels and drainage systems. Where drainage occurred depended on the water level of the lake and the position of the ice sheet. Figure 18.34 Glacial Lake Agassiz. This lake was an immense feature, bigger than all of the present-day Great Lakes combined. Modern-day remnants of this proglacial water body are still major landscape features. Lake Agassiz left marks over a broad region. Former beaches, now many kilometers from any water, mark former shorelines. Several modern river valleys, including the Red River and the Minnesota River, were originally cut by water entering or leaving the lake. Present-day remnants of Lake Agassiz include Lake Winnipeg, Lake Manitoba, Lake Winnipegosis, and Lake of the Woods. The sediments of the former lake basin are now fertile agricultural land. Research shows that the shifting of glaciers and the failure of ice dams can cause the rapid release of huge volumes of water. Such events occurred during the history of Lake Agassiz. A dramatic example of such glacial outbursts occurred in the Pacific Northwest between about 15,000 and 13,000 years ago and is briefly described in Figure 18.35. Figure 18.35 Lake Missoula and the Channeled Scab Lands. During a span of 1,500 years, more than 40 megafloods from Lake Missoula carved the Channeled Scab Lands. Photo by John S. Shelton/University of Washington Libraries. Pluvial lakes. While the formation and growth of ice sheets was an obvious response to significant changes in climate, the existence of the glaciers themselves triggered important climatic changes in the regions beyond their margins. In arid and semi-arid areas on all the continents, temperatures were lower and thus evaporation rates were lower, but at the same time, precipitation totals were moderate. This cooler, wetter climate formed many pluvial lakes. Pluvia equals rain. In North America, the greatest concentration of pluvial lakes occurred in the vast basin and range region of Nevada and Utah, Figure 18.36. By far the largest of the lakes in this region was Lake Bonneville. with maximum depths exceeding